Welcome to a new series on this YouTube channel. It is the first series on this channel about machine learning. This channel is all about machine learning, deep learning, reinforcement learning, and statistics. In the first episode, I would like to give you a very slight introduction into the history and idea behind AI, and afterwards we will work through a little optimization problem. This should serve as an appetizer, and in order to follow the series, I recommend that you have taken calculus and linear algebra on a university level. First of all, let's talk about some examples of machine learning usage in real life. For example, we all know Amazon's e-commerce site or Netflix, the streaming platform. They both use recommender systems which recommend products to the potential buyer or videos to the user, because Amazon wants you to buy more products and Netflix wants you to stay long on the platform. Other examples are game agents, chatbots like ChatGPT, or demand forecasting in stores like a supermarket. Nowadays, we are confronted every day directly with AI or even indirectly. The range of use cases is enormous, but what is actually the idea behind AI? In my opinion, an article about the history of AI named A Brief History of AI on the past, present and future of AI presented the idea behind AI in just one elegant sentence. Namely, a machine that is able to learn from external data and to use the learned knowledge in order to solve problems. I wrote the sentence down for you to carve it into your brain. Of course, we have to define what is learning in the context of machine learning, what is external data, what is knowledge, and how can we use these concepts in order to solve problems. We will see that in later episodes. But the ultimate goal in AI would be to create an artificial general intelligence, which is no longer distinguishable from a human being. This goes beyond problem solving. We really hope to understand the human intelligence and human emotions better by trying to construct systems that can overcome us human beings. A really insane goal, but I think it is worth trying. But when did AI actually emerge? It is very difficult to pinpoint exactly when AI emerged, but many people say that 1942, when Isaac Asimov wrote Runaround, where the 3 laws of robotics were stated, we began to dream of a system that is as intelligent as we humans are. 1950, Alan Turing published the article Computing Machinery and Intelligence, where the infamous Turing test was described, which is still a benchmark up until today. But the word AI was actually coined in 1956 by Marvin Minsky and John McCarthy. And the real hype around AI emerged during the last 2 decades, when big data and more powerful computers emerged. Since we will talk in this series about machine learning, let us draw a very simplified Venn diagram showing us where machine learning lies in the space of AI. Really keep in mind, this Venn diagram is really simplified and does not reflect the actual complexity of this research area. The Venn diagram looks like this. We have AI as the field, and as a subfield we have machine learning, and another subfield is deep learning. You might ask, what is actually the difference between AI and machine learning? And I invite you to find the answer online for yourself, what the difference could be. We will explore this in the future episodes. And as a side note, when having references like the sentence from this one article, I will link all the relevant links or references in the description below. Enough history for now. Let's start with our journey learning about machine learning. Okay, so let's do our appetizer. So we wanted to do an optimization. So first of all, what is optimization? And optimization deals with a set of techniques to maximize or minimize an objective function that can be subject to constraints. In our case, we want to look at a very simple polynomial function of 4th grade. We have no constraints, we have just our function. And our function is x to the power 4 minus 2x squared plus 4. And as you can see, it's a symmetric function. It's an easy to deal function with 2 minima, one sitting at -1, one at 1, and we have a maximum sitting at 4. And our goal is to find the minimum and maxima. So let's do that. So what do we have to do? Okay, you know from school, we have to take the first derivative, set it equal to 0, and then we just have to solve for x, right? So let's do that. So what is the first derivative? The first derivative is kind of simple. 4x cubed minus 2x, and the 4 drops. Oh, 4x, sorry. Okay, so far so good, and this should be equal to 0. What can we do? We can already extract 1x. And we get our first solution, x is equal to 0. Okay, so far so good. Now we can also have a look at what is written inside of the parentheses, right? We can also set it equal to 0. And we can solve it for x. And what we get is x squared is equal to 1, okay? And we know that x2, so that our two solutions is the square root of 1. And we get one solution with a plus and one solution with a minus. Square root of 1 is 1. So we have a solution of plus 1 minus 1. And in order to prove that we really have a minimum or maximum, what we have to do is take the second derivative. And now we just have to insert our solutions, and then we can see if it's greater or less than 0 in order to say whether it's a minimum or maximum. So, for example, here we have minus 4 when we evaluate our second derivative for x1. And we know that is our maximum. We can also see from the plot that this is indeed true. Okay. Let's quickly do it for the other two. So for x2, what do we get? 12, 1 squared minus 4 is 8, greater than 0. So we have really a minimum. And the same for x3, again 8, it's greater than 0, so again our minima. And as we can see that this is indeed true. If we have a look, we have one minimum sitting at minus 1, one at 1, and a maximum sitting at 4 for x equal to 0. Okay, so far so good. Next, we can ask ourselves, but what actually happens if we cannot solve this equation analytically? So for example, let's say we know our function, we can calculate our derivative of this function, but we are not able to solve this equation. How can we still find our minimum and maximum? And one technique is to do it iteratively, and that's what we're going to do next. In order to do the same iteratively, we have to find an update rule. And so how can we derive such an update rule? And for that, let's focus first just on the left part of the function, and only focus on the minima, which is sitting at minus 1. And in order to solve it iteratively, what we have to do is to pick a random point at any point in our function. But let's choose, for example, minus 1.5. So this will be our starting point. And let's zoom in a little bit into the part we are interested in, which looks like this. and we are starting here. We can also call it x0. And so what we want to do is we want to go into the right direction with our updates. So how does an update rule look like in general? Well, we could write something like this. X new should be proportional to x old plus minus some delta x. And this delta x is our correction factor, which we use in order to shift our old estimate towards a new value. And in this case, we know, since we look at the function itself, that we need to go into the right direction. So what we could do is use the first derivative, right? So we have a tangent, for example, which we can plot, and this would describe the slope at point x0. So, and we notice that the slope is negative in this case. So the first derivative evaluated at x0 is smaller than 0. Okay, so far so good. So let's write down, okay, our x new value should be our x old value, and now we don't know, should we take plus or minus the first derivative of f with respect to x at x old. And now, since we know that this is smaller than 0, and we know this is smaller than 0, and we want to move towards the right direction, towards the minima, we need a minus sign. Because this minus will cancel with the minus factor in the first derivative, because it's smaller than 0. So we will get something which is greater than 0. So we will indeed update our old value of x towards the right direction, to a greater value. For example, minus 1. But, okay, so this is our starting point. So let's insert our first x value. Our starting point is x0, and we said it's minus 1.5, okay. So let's calculate x1, which would be the new updated value. We got minus 1.5 minus the first derivative of x. Let me write it down so we have it as a reference. Okay. And we can also write it or simplify it a little bit. We can extract for x when we have it like this, right? And now we can insert 4 times minus 1.5 minus 1.5 squared minus 1. And what we get is 18. So as you see, we indeed updated our x value towards a greater value. That is what we wanted. But we went too far to the right? Because we know the second minima is sitting at 1 and we have 18. So we are too far to the right. So what can we do in order to correct this update rule? And what we can do is introduce a scaling parameter, alpha, which can be greater than or equal to 0. And what we need to scale is the first derivative, because this one is contributing in this case the most to this 18. So x old minus alpha, first derivative of x with respect to x old. And let's set our alpha value to a really small value because we overshoot it too much. So let's choose something like 0.01, for instance. And when we calculate again our update rule for x1, we get minus 1.5 minus 4, now scaled with 0.01 minus 1.5 minus 1.5 squared minus 1. What do we get? Minus 1.305. So that's already looking much better. So for example, now we could be like here. So we made a jump from our starting point a little bit further towards the right direction, but we are still not at the minima. But this is no problem because this is an iterative approach. So we can again insert our x1 into the new updated value x2. And now we have to evaluate our first derivative at x1. What we get is minus 1.268. So that's already much better. So we are again moving into the right direction, but still not at the minimum. But that's no problem. Now you can do this, calculate x3, x4, x5, x6, so on. And what you will see is we will get closer and closer to our minima. But it can happen that you never hit our minimum, but you could also oscillate between. And our minimum would sit in between and you would oscillate around the minima. This, for example, what would happen if we are starting here at the left, so towards the left from our minimum, and we would jump too far to the right. Now our first derivative here at this value x hat, let's call it like this, would be greater than 0. And if we have a look at our update rule, so x hat, we call it x hat, what would happen is this guy is now positive, this is also positive or equal to 0, and we have a minus sign in front of this. So it would be smaller or equal to 0. So we would jump back towards the left direction. But it could happen if your step size is not small enough that we will always oscillate around our minimum. But this is no problem because we want to get as close as possible to our minimum, but only within a certain kind of precision. Let's say epsilon. So if x tilde would be our minima, we want only to get as close as plus minus epsilon towards it. And that's good enough already for us. Because we are only trying to approximate it. And what we did before, when we didn't have our step size parameter alpha, was actually just a special case. So this update rule what we had was just x new, x old minus alpha, first derivative of x, at x old evaluated, just for alpha equal to 1. Yeah, and another special case would be alpha equal to 0. Then this would cancel, and we wouldn't update our new value. So, what can we do now in order to find the maximum? So let's have a look at our function again. And now we pick again. So now we want to find the maximum. So we pick again a random starting point. In this case, let's take a starting point slightly from the right from our minimum sitting at -1. Okay. And the principle behind this is the same as with the minimum. We would also work with the first derivative of f with respect to x at our starting point x0. Let's call it like this again. And now we know if we would draw a tangent line that this would be greater than 0. Okay. And our update rule would be x1, for example, is equal to x0 plus alpha and the first derivative. And now we know, okay, our first derivative is greater than 0, alpha is greater or equal to 0, and we have a plus sign. This is also greater equal to 0. Okay, so far so good. So we are moving towards the right direction. So we would indeed move towards the towards the maximum, right? We can ask ourselves now what would happen if we would go too far to the right direction and we would have a tangent looking like this, which first derivative would be smaller than 0. In this case, okay, let's write it down once again. So this is smaller than 0. This is still greater or equal to 0. So this is smaller than 0. So what would happen is we would update x0 towards a smaller value. So we would go towards the left direction. And this is also the behavior we want. Okay, so in principle, we derived 2 update rules in order to, one for finding minimas and one for finding maximum. Let's write them down. So we have xk plus 1. Let's write them down in a more general way. For k being an element of a natural numbers including 0. And this is known as gradient descent. And the other one we found for finding the maximum plus alpha, first derivative, is known as gradient ascent. And what do we notice when we compare both equations, both update rules with each other? So what we notice is the only difference is the sign, right? In one case we have a minus sign, in the other case we have a plus sign. Okay. How can we understand this change in sign in a different way? And another way to understand this little difference is to have a look at for example, again, a function. But let's take a different one. So for example, some kind of parabola, which has an intersection with the y-axis at 3 and has maybe a functional shape like this one, 2x squared minus 4x plus 3. And now let's calculate the first derivative again. And let's set it equal to 0. So what we get is x is equal to 1. Let's quickly insert into the second derivative. We get 4. This is greater than 0, so we know we are dealing with a minima. And now let's transform our function. With a relative minus sign. So, okay, let's say g of x is equal to minus f1 x. So what we get is a shape like this. This time its intersection with the y-axis is at minus 3. And g of x is minus f of x minus 3. So let's calculate again the first derivative. Let's set it equal to 0. What do we get as a solution? 1 again. What's the second derivative? inserted with x1 minus 4. This is smaller than 0, so we have indeed a maximum. Right? This maximum and this the minimum. And what we did is we turned a minimization problem into a maximization problem by just transform our function with a relative minus sign. And that is something we can actually always do. We can take a minus sign in front of our function, and we can turn a minimization problem into a maximization problem, and vice versa. So we arrived at the end of the first episode of this series about machine learning. We saw that it is fairly easy to derive the gradient descent optimization technique. This optimization technique is widely used in machine learning and deep learning. In the later episodes, we will investigate how to use this optimization technique in order to train our models. In the upcoming episodes, we will have a look at what is an objective function, why do constraints matter, what is actually a machine learning model, how can we train it. We will not only do mathematical derivations like today, but also code a lot and work together through interesting paper, rather old paper, but it doesn't matter, they're still so it's very good to know them or at least read them once. And if you're interested in that kind of content, stay tuned and let's see each other in the next episode.